Hi, everyone. Welcome back from the break. Thanks for joining us today. My name is Joshua, and we're really excited to show you some things that we've been working on. Sarah Bird is with the Azure AI team, and she'll be talking about protecting privacy and confidentiality with ML. I'll be watching the Q&A section for questions while Sarah presents, so please ask questions and make this session interactive. And with that, Sarah.
Hey everyone, thanks for joining our second session on responsible ML. In this session, we're going to talk about protecting privacy and confidentiality with ML. So we have a variety of capabilities that we've been developing in order to make it easier for developers and data scientists and organizations to develop machine learning more responsibly. The first set is what we covered in the previous session, which is about analyzing your models and being able to gain a deeper understanding in models. In this session, we're going to focus on the technologies that we have available for protecting people's privacy and being able to develop machine learning more confidentially. Finally, you can check out our websites and some of our additional on-demand resources to learn more about our last pillar, which is how do we control our machine learning process so that you can have complete control over the end-to-end life cycle and the resulting systems. A lot of these capabilities are new. They're being very actively developed, both in the research communities as well as in practice. However, there's a real need in many of these cases to think about these issues right now while we're developing machine learning. And so we wanted to develop our capabilities in the open source so that we could move rapidly, we could work directly with the research community, but we still want to expose these capabilities to customers developing machine learning as soon as they're ready. And so we take our open source libraries and then we integrate them in our platforms like Azure Machine Learning so that customers can easily find them during their development process and use them at the right points. In this session, we're going to talk about protecting people's privacy and their data. So one of the questions we need to think about when we're developing machine learning or doing analytics is, how do I use this data without revealing private information? You may not realize it, but when we use data, for example, to develop a model, we may accidentally reveal information about the underlying data set that we weren't expecting. For example, I could have a smart reply model where the model actually, memorizes some of the data points in the data set that occur less frequently. So if I type a rare sentence like my social security number is, the model might autocomplete with a social security number that I had seen in the data set, which could be a significant privacy violation. And so I really want to, be able to use data, but I have to think about privacy while I'm doing that. So we're going to dive straight into a demo here to just kind of better understand what I'm talking about. So for my demo, I'm using Azure Machine Learning because I really like to use the compute instances, which are a managed VM that makes it easy. Azure Machine Learning just updates the VM and I can just interact with it as a Jupyter notebook. So I'm going to jump over to my Jupyter notebook here, and actually I'm going to restart my demo here so we can see it from the beginning. So in this case, what I'm doing is I'm going to make a synthetic data set, but it's inspired by a type of report that the census releases called the PUMS data. And in this case, what I'm going to do is I'm just going to generate a synthetic version of the data here as if it were a published report. And I want to take this data and I want to do an income analysis. I want to understand how well is, what's the distribution of income for individuals at a given education level. So in this case, I'm going to click through some different plots here. And here's a histogram I have of what the income distribution looks like for individuals with a high school degree. And great, now I can take this, I can use it in my to make a machine learning model, or I could use it in my analytics or to put into a dashboard. However, it turns out that particularly if I combine this type of information with some additional information that may be public, I can learn a lot more from this graph than people realize. And so what I'm going to demonstrate here is how I can actually reveal more information from that published result. So in this case, I know a little bit more information about 2 people in my data set. My data set has 500 people, so it's not a significant percentage of the data set. But I'm going to take an off-the-shelf stat solver, and I'm going to use it to try to generate a data set that lines up with the published report. So the stat solver will find a satisfying result if it can find a data set that's consistent with the statistics that were published. So we're going to run my stat solver here in the notebook. And it was able to find a data set that would line up with the published results. And since we know what the real data set looks like, we can compare that reconstructed data set with the real one and see how well is the attacker doing. So in this case, of the 500 individuals in the data set, it was able to estimate 126 of them within $5,000 of the correct amount, right? So that could be a significant privacy violation, particularly if I know even more information and could be more sure about which ones I got correct.
Hey, Sarah, there's a question coming in about that demo.
Yeah.
So the question is, you mentioned that this is a SAT solver.
Mm-hmm.
So is this a database attack tool, and how do people get it?
Yes. Basically, it's just an off-the-shelf stat solver. It's not like specifically designed to attack databases. We're just using it to demonstrate how you could use it to satisfy constraints and basically reconstruct a data set. So it's just Z3. I just did a pip install. There's nothing particularly fancy going on. You can also check out this notebook in our GitHub repo under attacks, where we have a lot more explanation of what you're seeing. So if you really want to dive in and learn more about what I just demonstrated, you can check it out there. So with that, since I've been mentioning our GitHub repo, good news, there are some promising technologies that can help address this problem. So I'm really excited to talk about one of these, which is differential privacy. And the idea of differential privacy is we want to hide the contribution of any one individual in the data set so that we can't pull it out and reconstruct that private information like I just demonstrated. And so the way that differential privacy works is we're going to do this with 2 steps. In the first step, we are going to add noise to the output of that computation, and that helps hide the contribution of any given individual. The second thing is we need to calculate how much information was revealed in the query and subtract that from our privacy loss budget so that we make sure that we're not revealing too much information that then could be put back together. So I'm very excited to announce that as of today, we have released a new open source system for differential privacy with machine learning and analytics. The system is called White Noise, and we have been developing it with our partners at Harvard in the Institute of Quantitative Social Science and the School of Engineering and Applied Sciences as part of a larger initiative. And so the way the White Noise system works is you can put it on top of many different types of data stores or data sets, and then you query through the system, and we will manage the adding noise and calculating the budget so that you get it in as a result statistics or a machine learning model that is differentially private. So you have strong privacy assurances and don't need to worry about the types of attacks I just showed you. So actually, let's go, sorry, I'm clicking around too much. Let's go back to our demo here. And what I'm going to show you now is the next part, which is how do we use that system White Noise that we just talked about to actually protect people's privacy. So in this case, what I'm going to do in this cell is I've just regenerated those same reports, but this time I'm using the white noise system to output the report. And so it's going to add that differentially private noise so that we can protect individual contributions. So then the second thing I'm going to do now is let's go back to that same stat solver and let's try to do the same attack. In this case, we get a very different result, right? We get unsat, which means it wasn't able to find a data set which lines up with the published statistics, which means we don't have any guesses at people's income, which is great. However, it's not enough just to protect privacy, right? We could also do that by not using the data at all. And so we also want to look at how can we actually use this data to still do the analysis we were doing before. So I'm going to click through and I'm going to generate my histogram here. And in this case, we have results, right? And the private results, they look a little bit different than the non-private. They're similar in some ways, but also definitely a bit different. And so you can see differential privacy working here, and we can take these results and use them in our downstream machine learning or analytics.
Hi, Sarah. So there's some questions about the results there, like that middle bar. It looks like it's like there is no private answer. And so is this the sort of thing that you'd get different results if you ran it again? And is there an explanation for why some of those results are so different?
Yeah, you should check out the notebook in the GitHub. There's, you do actually, in this case, since we're generating the synthetic results, you get different results every time. So sometimes they're a bit more accurate or not. And what we're really seeing happen here is I'm using an extremely small data set. As I said, only 500 individuals. And the reason that we're using such a small data set here was to demonstrate that attack in the notebook. However, differential privacy, for smaller numbers, you're going to see more noise added, which could be okay if the particular analytics that you're doing can tolerate that amount of noise. However, if you're using a larger data set, it might be that the noise that's added is, in fact, basically negligible. So if we look at our utility curves I have here, what you can actually see is I'm going to generate two different plots. So this first plot is looking at the accuracy of the private and non-private results for the larger groups in the data set, which are just over 100 since my data set's not that large. And you can see that the results are somewhat accurate, not perfect as we just saw in the histogram. However, if I look at this other chart, you're really seeing differential privacy at work here, where what we've done, what you can see is like the results are all over the map for small groups. And the reason is we don't actually, as far as privacy is concerned, we don't want the results for very small groups to be accurate, because that makes it much easier for us to see their contribution in the data set. And so we're seeing the system do actually what it's designed to do here, which is add noise to hide individuals. So it's really a case where what we want to do is use it for those larger scale sort of questions, definitely larger than the size I have here in the data set. So I'm going to jump back here and I'm going to go and say, differential privacy is an emerging technology. And so we're developing the white noise system as part of a larger initiative that was started by Harvard, which is called OpenDP, Open Differential Privacy. And the idea is that we want to create a community around these technologies so that we can actually develop them, push the state of the art, and really try to make them work in practice so that privacy technologies like differential privacy can be used in more problems. So a lot of you are probably worried now that you're going to just, have terrible quality data after what I showed you. But the vision here really is that we want to use differential privacy to allow us to actually use data that we are not able to use right now due to privacy concerns, right? If you imagine a health data set, it might be that we want to be able to do machine learning on top of that in order to better understand, some of the key questions in healthcare. However, and that can really help people. However, right now, might be very concerned to let anybody even use that data for fear of leaking anyone's individual healthcare record, which would be a very bad outcome. And so this is a case where we really see the promise of this technology as enabling us to use more data to solve society's hardest problems. So I'm going to shift gears a little bit here and talk about another class of emerging technologies we have that help you do machine learning more confidentially. So in this case, we're investing in a range of technologies to allow you to have higher levels of kind of guarantee of confidentiality in your process. So the most straightforward one is the case where I want to build a model, but I don't want to let the data scientists see the data. Maybe to protect the data scientists, to protect the confidentiality of the data. And so in this next year, we'll be releasing this in Azure Machine Learning, where a data scientist can generate a model, and then you can actually have the Azure Machine Learning train it without giving the data scientist access to the data. We also have capabilities which you can learn more about in our on-demand videos in Channel 9, which are basically doing encrypted machine learning, either training a model that's encrypted or doing inferencing encrypted, which is leveraging the hardware built on top of Azure Confidential Computing. However, today I'm going to talk about a technology that you can use right now, which is homomorphic encryption. And the idea with homomorphic encryption is I want to do machine learning inferencing, and I want it to be encrypted, but I don't want to rely on hardware like what we were just talking about. So in this case, you can actually do the computation while keeping everything encrypted. So I can add encrypted 1 to encrypted 2 and get encrypted 3 back. And so we have another open source library that's been out for a few years called Microsoft Seal that has many great implementations of homomorphic encryption algorithms. And what we've released today is some sample notebooks showing how you can use Seal in combination with Azure Machine Learning to do this homomorphic inferencing. So in this case, I can send a prediction to the model, but my request is encrypted and the response is encrypted, and we didn't have to unencrypt it to calculate the inferencing. So you can get your prediction back without ever having exposed the features that you sent to the model for prediction. So we have a lot of great resources that you can check out if you want to learn about any of these technologies. You can go to the White Noise GitHub. We have Seal. We have those notebooks to show you how to use it in Azure Machine Learning. And we have a lot more sessions if you want to learn about AI at Build, including additional sessions on responsible ML for analyzing your models and also for interpreting your text models. So with that, I'm really excited to say that our partners at Harvard that have been developing the white noise system and the OpenDP initiative are going to join for the Q&A, so you can ask live questions to any of that. So Gary and Salil, welcome. And with that, I'd love to open it up to questions.
Thank you, Sarah. So we'll start with the first question. You just showed two different ways to protect the privacy of your data. And so the question is, why would somebody use one versus the other? Are these like competing technologies?
Yeah, it's a really good question. And the answer is there's a lot of innovation happening. And so people are exploring, both in research and practice, a wide range of technologies, and each of them has a little bit of a different shape. And so they solve, in some cases, overlapping but slightly different problems. And so the right one for your particular problem is going to vary on the parameters of your problem and how much overhead and what threat model you want to look at. But in the case particularly of the confidentiality versus privacy, the confidentiality ones are really aimed at keeping that process or that model confidential, but it doesn't say anything about what happens when you use the model. So if we think back to the smart reply example I gave, you can still have that same thing happen with your encrypted model, right? The response could still be giving private information about the underlying data set, where that's the problem that differential privacy solves. And so what we see in a lot of cases is the most sensitive applications, you're really using a combination of these, right? You want to keep the data as confidential as possible while you're using it for training and inferencing, but then you also want to use privacy measures to make sure that you're not revealing that data when you go and use it.
Awesome, thank you. Okay, so another question, is OpenDP approved by government regulators? And I'll direct this to Gary, I guess.
Hi, everybody. Thanks for having us. Differential privacy is a mathematical equation, so they don't approve mathematical equations. But as a technological solution to a political problem, it actually does work. In fact, it's pretty much the only thing that works that enables you to get insights from a large set of data when the individuals must be protected. So yes, it actually is quite useful at convincing regulators all over the world in different ways.
Great, thank you. That's a great answer. Okay, so next question. What's the difference between OpenDP and white noise? And I'll direct this to Salil.
Thanks for having me too. So white noise is the first of the OpenDP systems. It's something that we've done in partnership, Harvard and Microsoft together, and we're really excited about that as a model for future industry academic collaborations to try and bring all the advances that are happening in the research literature to practice and to help in using data to solve important societal problems. But what OpenDP is, it's a larger community effort aimed to bring in the entire differential privacy community, those who are researchers in academia, as well as those in industry and government who are trying to bring differential privacy to practice, and to share our collective insights with each other to build this larger, trustworthy suite of differential privacy tools, and that can grow and advance as the research in this field continues to advance, which is happening at a very rapid pace.
You know, Josh,
Awesome.
if it's okay, could I add something? So
sure,
yes, this differential privacy is going to do we're going to implement the things exactly as Salil says, and it does satisfy regulators. But of course, not providing any data at all would also satisfy regulators. The interesting thing about differential privacy is it also satisfies the users, right? It also satisfies us as statisticians, as social scientists, and it satisfies people in companies who try to use it. So we saw the noise that Sarah showed us, and that seemed a little scary. But if we were just doing a survey, and we said, here's the population, what we would like to know who everybody's going to vote for in the next presidential election. And instead of asking everybody, we took a random sample of only 1,000 people. And if you look at it, it actually differs from the truth. And if you look at a different sample, it will differ from the truth, right? And so we say, well, oh my gosh, how is that useful? Well, it's useful because the properties of those samples we know mathematically. And on average, we're going to get the right answer. And exactly the same thing is true of differential privacy. So it's useful to regulators because it convinces them. And it's useful to us as social scientists because we solve problems in the public good. And I think it will be useful to many of the people listening today because they'll be able to use data that they would never be able to touch otherwise.
Great, thank you. All right, so this one I'll direct to Sarah. And so the question is, you did all of your demos using Azure ML notebooks, but since this is about sharing data, does this work if somebody wants to share with somebody who doesn't have Azure?
Yeah, so the white noise system is completely open source. We've built it as a collection of flexible building blocks, so you can plug it into different systems and hopefully have kind of the right shape for your system. One thing that I didn't mention that is worth mentioning here, though, is the vision is that you'll be able in the future to use this system in cases where, for example, two parties don't trust each other. Like I'm the data owner and I want to let analysts use this, but I don't want to let analysts directly use the data. And that's still a scenario that we're aspiring to right now. What we support in the white noise system is basically you have access to the data, but you want to make sure that when you use it, either for, take your model out or take your statistics out, that you don't have to worry about any of the privacy concerns. And so right now, yes, you can use it in kind of any system you want, but it needs to be an environment where you trust the analyst.
All right, great. Okay, so this is a follow-up on the question about white noise versus OpenDP, and I will direct this to Gary. So who can join OpenDP?
Oh, we would love for anybody interested, either in the theory or the application or the software, to absolutely join us. There's lots of ways of joining us. Really, it's a community. We need to know in detail what the kinds of applications are that would be useful to you. And we also need to know all the way at the other end of the continuum what the theorists can produce. And I guess the continuum has a third point, so we'll make it a triangle. For statistical usage, we need to know exactly what the properties are of the analyst. So if you're interested in any of those things, including even the legal applications of this for regulators, we'd love for your participation.
Great, thank you. All right, so this one, so there's a lot of questions about the variance, the variance versus the accuracy versus privacy trade-off. And some of these questions seem to be geared towards the mechanics of how does a user, how does the analyst who's building these differentially private reports, how do they know how much noise to use? How do they calibrate that noise? And I'll direct this to Salil.
Yeah, great. So differential privacy has tunable knobs. One of those knobs is tuned to how much privacy protection you want or are required to provide to your data subjects. And that's going to determine what kind of noise infusion is done and the quantity of noise that's introduced. But the amount of noise will also depend on other things. It'll depend on how big a population, as Sarah talked about earlier, you're doing your analysis on a larger population. The effect of the noise for privacy will be drowned out by other forms of noise, like the sampling error that Gary talked about, the dimensionality of your data, the complexity of the model that you're running. And one of the things that we are working on doing in OpenDP is building differential privacy tools that will become a part of white noise that will expose that very directly and in interpretable ways to end users. In the meantime, what an end user can also do is do what Sarah showed us, which is run experiments on synthetic data. And that gives you an idea of how much noise is being introduced for a particular kind of analysis and level of privacy protection.
And I just want to add, you can, if you go to the GitHub white noise samples, we do have a section that helps you kind of understand what these utility curves could look like. And the other thing is we have an example there and in the blog where you can also explicitly specify how much budget you're using for a particular query, which has a direct effect on sort of how much noise is being added.
All right, great. And it looks like we have about 1 minute left. So so this one's for Sarah. Where should people go for next steps?
So we have a lot of great resources. There's more videos on demand on Channel 9. You can check out us directly on the White Noise website and the White Noise GitHub. Also, there's resources for OpenDP. And then in Azure Machine Learning, you can learn more about white noise as well as a whole variety of the other responsible ML tools that we've released. We're so happy that you have joined the session, and we hope you find it useful. Join the OpenDP community, check out white noise. It's very early, so we would love feedback and usage and contributions. So we hope to meet you on GitHub.